Centuries ago in Asia Minor, near the city of Magnesia, travelers found bits of rock that attracted iron. Years later, the unusual behavior of the rock, or magnetite, when its movement was unhampered, led mariners to rely on something beside the sun, the moon, and the stars to guide them home. In 1819, an experiment at a Danish university revealed an unusual fact about electricity. Hans Ørsted showed the existence of a magnetic field around a conductor. Coiling the conductor increased the strength of the field. The magnetic field from the coil carrying electric current and the magnetism of various materials started the world on the way to an electromagnetic revolution. What is magnetism? You can't see it. You can only see the way it affects something else. There are several kinds of magnetism. Each kind is related to the properties of electrons, the fast-moving outer parts surrounding the atoms of all substances. The weakest kind of magnetism is diamagnetism. This arises from changes in the orbital motion of the electrons when a diamagnetic substance is near a strong magnet. The change of motion produces a magnetism, or a magnetic moment, that opposes the field of the strong magnet. Graphite is diamagnetic and is repelled. Another form of magnetism is paramagnetism. This is moderately weak. The orbiting electron produces a magnetic field that's like a bar magnet, or an orbital magnetic moment. While orbiting, all electrons also spin, and the spinning electron behaves like a bar magnet too. Usually the orbital magnetic moments and the spin magnetic moments from many electrons around an atom pair off with their own kind in an up-down combination, canceling the total magnetic moment of the atom. The atoms of a few substances have unpaired magnetic moments left over. These are the paramagnetic atoms, each a tiny magnet. They more or less ignore their neighbors. But a paramagnetic substance like manganese is attracted to a magnet. Ferromagnetism is the strongest form of magnetism. It's found in iron and steel. The free iron atom is surrounded by electrons orbiting in several outer shells. Momentarily halting all movement to examine the shells, we find an uneven number of spinning electrons in the third shell, 9 up and 5 down. This leaves 4 electrons with uncompensated upspins, making the iron atom a good paramagnetic atom. Provided the temperature isn't very high in the crystalline framework of solid iron, the atoms are close enough to feel each other's presence through a strong interatomic force. They line up, so all are parallel in a small region. But impurities in iron and steel create structural breaks that hinder overall alignment. The aligned areas inside these breaks are called domains. When an outside magnetic force is applied, the haphazard magnetic force directions of the domains are realigned, and the domains grow in size to include all the atoms in the object. In a permanent magnet, the domains stay aligned. In ordinary iron, they don't. These are principles that govern the use of magnetism and magnetic materials. Now, let's look at some everyday applications. Iron filings sprinkled above a magnet reveal the lines of force surrounding the magnet's north and south poles. Unlike poles attract, and like poles repel. This principle is used in loudspeakers. A coil surrounded by the lines of force of a powerful permanent magnet moves back and forth in time with alternating signals from an amplifier. The faster the signals arrive, the faster the cone vibrates, producing different notes and effects. tape recording that stores music and voices is a magnetic iron oxide-coated ribbon with areas of varying magnetization. Magnetic ferric oxide particles floating in suspension will reveal the magnetic information because they are attracted by the fields from the tape. The electronic pulses that build a television picture also may be stored on tape. Spinning recording heads place magnetic picture information in the middle of the tape, and stationary heads put sound and other information along the edge. Digital information used by computers is stored on magnetic tapes and discs in the same basic manner. If a recording or pickup head touched the rapidly spinning storage discs, the disc plating would soon wear away. Special heads take off, something like a low-flying plane, and glide only thousandths of an inch above the disc, depositing and retrieving information. Inside the computer, wires crisscrossing through small ferrite cores create magnetic fields that magnetize the cores in one direction or the other. The polarity of the magnetization in the core determines the information stored at that point. Often millions of cores are used in one computer. Electromagnetism is limited to applications that require a power supply or a source of electricity. But permanent magnets work without wires. And without permanent magnets, many contented cows might be downright ornery. Farm pastures contain all kinds of hardware, chips of steel from damaged tractors, bits of wire from broken fences. Hungry cows gulp down the hardware with the hay. This leads to a condition called hardware disease. The wandering iron and steel irritates the cow's stomach lining. A simple magnet solves the problem. A balling gun is used to place the magnet in the cow's first stomach or reticulum. And the magnet attracts and holds any bits of steel and iron in one spot. It remains in place for the life of the cow. Cows aren't the only hardware victims. Curious youngsters sometimes swallow the wrong things too. But people's stomachs don't take kindly to cures for cows. Doctors now have a device that can be lowered into a patient's stomach, then positioned with the help of a fluoroscope over the swallowed magnetic object. Permanent magnets are always on, ready to attract something. This medical probe is switchable. It's on when touching an outer pole and off when pulled back into a surrounding shield. This switchable feature lets a doctor move or rotate a sharp object before lifting it from the patient's stomach to avoid scratching delicate linings as the object comes up. A great deal of input power is wasted by the fixed resistance of coils in ordinary electromagnets. Superconducting materials, on the other hand, have zero resistance. Niobium tin tape becomes superconducting when lowered into liquid helium at temperatures approaching absolute zero, or minus 459.6 degrees Fahrenheit. An extremely strong field is created, strong enough to extend beyond the walls of the liquid helium container, affecting any magnetic object brought into the area. Super strong permanent magnets are available too. With like poles facing each other, ferrite magnets will support some weight across a given air gap. And alnico magnets can bear a bit more. Newer magnets made from an alloy of samarium and cobalt are super strong. Same air gap, but much more weight. Now, designers can build more efficient, smaller motors and other devices with more efficient and smaller magnets. From the rocks of magnesia to yet undiscovered applications, an invisible force guides global activities and grips the imagination.